Star, also known as Y, and Delta are common voltage configurations used in three-phase electrical systems. Each configuration offers distinct characteristics and is suited for different applications. Let's delve into the details of each. First, the star, or Y, configuration. In a star configuration, the terminals of each phase are connected to a common neutral point, forming a Y shape. This configuration provides a neutral point, which allows for the connection of single-phase loads and grounding. However, the voltage in a star configuration is lower than in other configurations. Specifically, it is approximately 57.7% of the line-to-line voltage. A practical use of the star configuration is in low-voltage distribution systems, lighting circuits, and for providing neutral connections. Now, the delta configuration. In a delta configuration, the terminals of each phase are connected to the other two terminals, forming a triangle shape. This configuration provides a higher voltage than the star configuration, equal to 100% of the line voltage. However, a delta configuration does not have a neutral point. A practical use of the delta configuration is in high-power distribution systems, motor drives, and for applications where a higher voltage is required. The Y configuration is essentially the same as the star configuration. The terms are often used interchangeably. It refers to a three-phase system connected in a Y shape, providing a neutral point but with a lower voltage than the delta configuration. Its practical uses are similar to those of the star configuration. There are other voltage configurations as well. The zigzag configuration is a variation of the star configuration where two of the three phases are connected back-to-back to reduce harmonics. The Schottky configuration is a transformation used to convert between two-phase and three-phase power. Now, the key differences and practical uses. In terms of voltage, the delta configuration provides a higher voltage than the star configuration. In terms of a neutral point, the star configuration provides a neutral point, while the delta configuration does not. Regarding harmonics, the zigzag configuration reduces harmonics. Regarding power distribution, the delta configuration is used in high-power distribution systems, while the star configuration is used in low-voltage distribution systems. For motor drives, the delta configuration is often preferred for high-power motor drives. And lastly, the star configuration is used for connecting single-phase loads and for providing a neutral point for grounding. To summarize, firstly, the star configuration provides a neutral point, allowing for single-phase loads and grounding, but has a low voltage. Secondly, the delta configuration provides a higher voltage but does not have a neutral point. Thirdly, the Y configuration is similar to the star configuration and is often used interchangeably. Fourthly, the zigzag configuration reduces harmonics. Fifthly, the delta configuration is suited for high-power applications, while the star configuration is suited for low-voltage applications and single-phase loads. When selecting a voltage configuration, consider the voltage requirements, the need for a neutral point, and the presence of harmonics. For low-voltage distribution and single-phase loads, the star configuration is a good choice. For high-power applications requiring higher voltage, the delta configuration is preferred. If harmonic reduction is a concern, the zigzag configuration may be considered. Keep in mind that the specific application and load requirements will dictate the most suitable voltage configuration for a given electrical system. When working with electrical systems, always adhere to safety protocols and consult with qualified professionals to ensure safe and reliable operation. The selection of the appropriate voltage configuration is crucial for efficient and safe power distribution. Understanding the differences between star, delta, and Y configurations enables engineers and technicians to make informed decisions in designing and maintaining electrical systems. These configurations are fundamental concepts in electrical engineering, and a solid understanding of their characteristics and applications is essential for anyone working in the field of power systems. In addition to the key differences already mentioned, there are other factors that may influence the choice of voltage configuration. For example, the impedance of the source and load can affect the voltage regulation and efficiency of the system. In some cases, a combination of star and delta configurations may be used to optimize performance. For instance, a transformer may be connected in delta on the primary side and star on the secondary side to provide both high voltage and a neutral point. The choice of voltage configuration can also impact the protection scheme of the electrical system. Star-connected systems are generally easier to protect against ground faults, as the neutral point provides a convenient reference for detecting fault currents. Delta-connected systems, on the other hand, may require more sophisticated protection schemes to detect ground faults. In some industrial applications, the delta configuration is preferred because it can provide a higher level of fault tolerance. If one phase of a delta-connected system fails, the other two phases can continue to supply power to the load, albeit at a reduced voltage. This can be important for critical loads that cannot tolerate interruptions in power supply. The selection of voltage configuration can also be influenced by the available equipment and infrastructure. In some cases, it may be more cost-effective to use a particular configuration because the necessary transformers, switchgear, and other equipment are readily available. The choice of voltage configuration is not always a straightforward decision. It requires careful consideration of a variety of factors, including voltage requirements, load characteristics, impedance protection, fault tolerance, and cost. A thorough analysis of the specific application is essential to ensure that the optimal configuration is selected. It is also important to note that the standards and regulations governing electrical systems may vary depending on the location. Engineers and technicians must be familiar with the applicable codes and standards to ensure that the designs comply with all requirements. In addition to the traditional star, delta, and Y configurations, there are other more specialized configurations that may be used in certain applications. For example, the open delta configuration is a variation of the delta configuration that uses only 2 transformers instead of 3. This configuration is less expensive than the full delta configuration, but it has a lower capacity. The 6-phase configuration is another specialized configuration that is sometimes used in high-power applications. This configuration provides a higher power density than the 3-phase configuration, but it is more complex to implement. The choice of voltage configuration is an important aspect of electrical system design. A well-designed voltage configuration can improve the efficiency, reliability, and safety of the system. In summary, when choosing between star, delta, and Y configurations, consider the following: the voltage level needed for the application, whether a neutral point is required for single-phase loads or grounding, the potential for harmonics and the need for mitigation, the power distribution requirements, whether high power or low voltage is needed, and the type of motor drives being used, considering the power requirements. Also, consider factors such as fault tolerance, protection requirements, available equipment, and local standards. By carefully evaluating these factors, engineers can select the most appropriate voltage configuration for a given application and ensure the safe and efficient operation of electrical systems.